Okay, so let's start by doing problem 1A here. So problem 1 says, consider the global energy balance diagram below from Wild et al. 2013. This is the figure that was sort of the central character in our global energy balance lab at the beginning of the semester. And for this question, it asks us to determine the following properties of the global energy budget. And problem A is asking us to calculate the net radiation at Earth's surface, and it goes on to say that net radiation is the net total of the shortwave and longwave energy fluxes. So the important insight to this problem is that we need to be careful in making sure that we understand what is coming into and what is leaving the Earth's surface in terms of the energy fluxes. And we need to be very consistent with how we define the signs. So as long as we do that, as long as we're very careful about determining what comes in and what goes out, and assigning the proper and a consistent sign for each of those fluxes, then this problem should be somewhat straightforward. So we'll start off here by saying, okay, so problem A is asking us to find the net radiation at Earth's surface. Okay, so if we look at our diagram right here, and we look at the radiation fluxes we have, they are here in yellow and in orange, okay? And so for our solar or shortwave radiation, we have 185 watts per square meter coming in. We have 24 watts per square meter that is reflected back out into the atmosphere. And an important insight here is that we're further given that the net solar or net shortwave radiation at the Earth's surface is 161 watts per square meter coming in. So if we do shortwave or solar, and we look at the influx and the outflux, coming in we have 185 watts per square meter. Leaving, we have 24. Or the other insight that we can gain from the figure is that the net of those, the sum total of those, is 161 in with 0 out. Right, so if you subtracted 24 from 185, you would just get 161. So the figure is sort of helping us skip ahead a step, as it were. So if we look at the long wave or thermal radiation in the figure, we see that we have 342 watts per square meter coming in and 398 watts per square meter leaving. So what's coming in is 342. What's leaving is 398. Okay. So what comes next is just a simple summation of these terms, okay, to get the net incoming and net outgoing radiation. So for the incoming radiation, we just sum these two numbers here. So that gives us 3, 0, so 503 watts per square meter incoming in both the shortwave or solar and long wave or thermal radiation. Okay, so for the outflux, this is pretty simple because this is a 0 for the solar and this is 398 for the thermal. So that's 3, 398. Okay. So from here, this is just a relatively straightforward calculation, but what is really important here is that we need to be very careful about how we define the sign. So we are going to define, again, the sign for the incoming radiation as positive because it tends to warm the surface, and the outgoing radiation flux as being negative, meaning that it tends to cool the surface. Okay, so this operation just winds up being that we take 503 positive and subtract 398, and these are both watts per meter squared, watts per meter squared, square that. Okay, and when we do this calculation here, what we wind up with is 581 watts per square meter. Okay, so, and this is what we would refer to as our net, or the net radiation at Earth's surface. And so what this says is that net between the solar and thermal radiation fluxes that are both entering and leaving Earth's surface, we have a net 185 watts per square meter. Okay, now let's go ahead and move on to question B. Question B is asking us to determine the net long-wave radiation in Earth's atmosphere, and it further asks us what the sign of that net long-wave radiation flux implies. Okay, so here our system is a little bit different. So in question 1A, our system that we were looking at was Earth's surface, but now what we're looking at is Earth's atmosphere, and in particular we're only being asked to look at those arrows here, those long-wave radiation fluxes in orange here. Okay, so again, this is a question in which, if we are very careful about determining which fluxes are coming in and which are going out, it can go a long way towards getting us towards the right answer. So question B here is to determine the net long wave in Earth's atmosphere. And so if I'm looking here, so if this is my system here, if I'm drawing a box right around this cloud in the vicinity of these orange arrows on the right here, again, I'm just going to write what's coming in and what's going out. So what I have coming into the atmosphere is this 398 watts per square meter that is emitted from Earth's surface to Earth's atmosphere. So that is an influx in the amount of 398 watts per square meter. Okay, and I don't see any other orange arrows pointed towards the atmosphere. All of the other orange arrows are pointed away from the atmosphere, meaning that they are outgoing fluxes. So one is pointed from the atmosphere towards the top of the atmosphere, the TOA, and the other arrow here is pointed from the atmosphere to the land surface. So both of those are outgoing fluxes, and we are going to account for both of them. So we have a 239 and we have a 342, and that is the entirety of all of the long wave or thermal energy fluxes coming into or going out of the atmosphere. So now what we can do again is just sum the incoming long wave radiation fluxes, and the answer here for the total incoming is 398. Okay, and we're going to do the same for the outgoing fluxes. So again, here we are going to do this summation. So I have 9 plus 2 is 11. Carry the 1, that gives me an 8. And this gives me a 5. So here I have 398 watts per meter squared coming in, 581 watts per square meter leaving. Again, I need to be very careful about the signs of each of these when I'm doing this net differencing. Okay, so again, I'm going to define incoming fluxes as positive because they tend to warm our system here being the atmosphere, and I'm going to correspondingly label outgoing fluxes as negative. Okay, so when I take my positive 398 watts per square meter and I subtract 581 watts per square meter, I get a value of minus 183 watts per square meter. So the question also asks us to comment on the nature of the sign of our answer here. So we got an answer of minus 183 watts per square meter. So what that says, again, just to be clear, is that there are 183 watts per square meter more leaving the atmosphere through long wave radiation than are coming into the atmosphere as long wave radiation. So there's sort of two important things that we can take away from this value of minus 183. The first is that the value is not zero, so the fluxes do not balance. Okay. The second is that the sign is negative, and because of the way that we defined incoming and outgoing radiations with the sign, that means that the negative sign implies that long wave radiation serves to cool the atmosphere because there are 183 watts per square meter leaving. So long wave or thermal radiation tends to cool the atmosphere.